Renaissance puzzle number 224, Keville's Conundrum. Have you heard of Zeno's paradox about Achilles and the tortoise? Zeno of Elea was a Greek philosopher who liked to pose philosophical problems called paradoxes. His most famous paradox deals with a foot race between the Greek warrior Achilles and a tortoise. It goes like this. One day the tortoise challenged Achilles to a foot race. Achilles laughed and said, "Don't be ridiculous. You know I will win. I can easily run 10 times as fast as you." But the tortoise replied, "If you'll give me 100-meter head start, I'll bet you 100 drachma that you can't catch me." 100 drachma, eh?" said Achilles. "Okay, I accept your challenge." So 2 starting lines were marked off 100 meters apart, and the runners took their marks. The official, Stavros Papadopoulos, banged a gong to start the race, and the runners took off. Just as he boasted, Achilles was running 10 times as fast as the tortoise, but when he had run 100 meters to reach the tortoise's starting line, the tortoise was now 10 meters ahead. So Achilles ran the additional 10 meters, but then he found that the tortoise was 1 meter ahead. So Achilles ran the 1 meter and found that the tortoise was now 10 centimeters ahead. You see the pattern. Imagine the excitement in the sportscaster's voice in the next stages. "The tortoise is leading by 1 millimeter, but Achilles is closing in. Now the tortoise is ahead by 100 microns. Make that 10 microns. And Achilles has closed the gap to 1 micron. And now it's just 100 nanometers. Great Zeus, what a race!" And so it proceeded ad infinitum, with Achilles getting ever closer to the tortoise, but never quite catching him. Perhaps you see the error in this reasoning, though it has puzzled some great minds. I will leave it to you to figure out what is wrong with it. But what I really want to talk about is a different paradox that I noticed while working on the area of the triangle puzzle posed by Derek. I have not come across any discussion of this paradox before, and it may not be quite correct to call it a paradox. So I will vainly call it Keville's Conundrum, in the hopes that it becomes famous like Zeno's paradox. By the way, if you can find this published elsewhere, I will award you 2 Renaissance points and retract my eponymous title for the paradox. Let's start with the formula for the area of a triangle. You were probably taught in elementary school that the area of a triangle is equal to 1/2 the base times the height. But how do we know that's true? Let's look at a rectangle of width W and height H. The area of this rectangle is the width times the height. Now let's draw a diagonal line from corner to corner on the rectangle, dividing it into 2 identical right triangles, A and B. Since the area of each of these triangles is half of the rectangle area, we know that their areas are 1/2 their base times their height. So we have shown that the area formula is true for a right triangle. But what if the apex of the triangle is nearer to the middle of the base? It's not difficult to adapt our special case proof to this case. First, let's draw a perpendicular line from the apex to the base, dividing our large triangle into 2 smaller right triangles of area A and B. We don't know the base lengths of these 2 new triangles, so let's call the base on the right L. Then the base on the left is W minus L. The total area is the area A plus area B, which is equal to 1/2 W minus L times H plus 1/2 L times H. Distributing terms, we get this, which is equal to 1/2 the base times the height. So we have proven that the area of a triangle is 1/2 the base times the height for the right triangle and the triangle with the apex above the base. But what about a triangle with an overhanging apex to one side of the base? Is the area formula valid for this case? If you believe it is, then give a proof as was done for the first 2 cases. If you believe it is not valid, then prove that it isn't. But before you get on with that task, I'd like to show you something that may influence your thinking. Let's start with an isosceles triangle with base B equals 6 inches, adjacent sides A and C, and a height of 2 inches. Its area is 1/2 times 2 inches times 6 inches equal to 6 square inches. Now let's rotate the triangle so that side C becomes the base. It now has a new base width and height, but the area is still 6 square inches. Here's where things get interesting. Now I'd like to stretch your mind a little bit. Here we have the same 6 square inch triangle formed by a rubber band with 2 nails defining the corners of the base. And this dotted line showing the height. According to the formula, if you can believe it, we can stretch the rubber bands such that we move the apex along this line and the area inside the triangle does not change, because the formula says the area is 1/2 the base times the height, and we are not changing the base or the height. Can you believe that? So we can stretch this as far as the rubber bands will allow us. If the rubber bands were infinitely stretchable, we could stretch this 1,000,000 miles or to infinity and beyond, and the area inside the triangle does not change. It remains as 6 square inches. Can you believe that? The formula says it's true. So if you wanted to paint the inside of this triangle, all you need is 6 square inches of paint. Doesn't matter if you stretch this to Alpha Centauri. So here we are once again with our 6 square inch triangle, but this time we're back to the original orientation with the long side as the base. Now if we stretch that side in this direction, we can stretch the baseline as far as the rubber bands will allow again, but now, unlike our previous situation, we're increasing the area inside the triangle. So if I increase the base to infinity, the area inside the triangle goes to infinity. How can that be that if we stretch this apex off to infinity, the area stays a constant 6 square inches, but if we stretch this side, the area grows infinitely? That, my friends, is Keville's conundrum. So to summarize, there are 2 parts to this puzzle. Part 1 for 1 Renaissance point. Prove or disprove that the triangle area formula, area equals 1/2 the base times the height, is valid for the case where the triangle has an overhang as shown below. And part 2 for another Renaissance point, explain how it is possible that stretching the apex of this triangle to infinity does not increase the area inside the triangle. Happy Renaissancing!